In our last video, we had a look at how triangles can be divided in proportion and how helpful knowing that proportion is in terms of solving for lengths and size. And now another way that proportion slips into our syllabus is when it comes to similar triangles. So in grade 9, we were introduced to similar triangles, or in fact similar shapes, where the angles are all the same, but the size can differ. And so we learned then that you can have the same size angles and sides in proportion. And so that theorem is going to come back in full force now in matric. And so here is the theorem. If two triangles are equiangular, in other words, equal in angles, then the corresponding sides are in proportion and consequently the triangles are similar. So what we're going to need to get good at doing is proving similarity and then using that to determine the proportions of different triangles. So before we dive into too much application, I want to check that our foundation is in place. So if you have a look here, we've got two triangles, triangle ABC and triangle CDE. Let's go alphabetically. And those two triangles, let's have a look at what we would do if we were required to prove them as similar triangles. So there's the one and there's the other one. Okay, the first line that we need, or first statement that we need to make, is just saying which triangles we are working in. So in triangle ABC and triangle CDE. Okay, so ABC is the blue triangle, and so every statement I make needs to start with the blue triangle, and then we go over to the red triangle there. Okay, now we want to look at what is equal. So the first thing I see is that here's an x and there's an x. So that's going to be the first thing. Some students number their reasons. You don't have to do that, but it helps. We need to have at least two equal angles, and then the third one is automatically going to be equal because the interior angles of every triangle add up to 180. Okay, so the first thing we're going to do is we're going to say in the blue triangle, angle A is equal to the angle E there in the red triangle. So angle A is equal to angle E, and that was just given to us. Okay, and we could even say equals x, I suppose. So we don't need to give too much of a reason there. They literally told us that. Okay, now we need another angle that is equal. So I'll have a look. I've used A and E. So it's either going to be B or C over here, and C and D over here. So let's number these C's, because to me that seems like the most obvious choice. I am noticing a bit of an X shape down here. Okay, and that takes me way back to vertically opposite angles, that one there and that one there. Okay, so we start by listing the blue. So angle C4 is equal to angle C2, and those are vertically opposite angles. And then we can even just say, therefore, the last one, angle B, we can write this as number 3, is equal to angle D, and that's the third angle of a triangle. Okay, and now I've proven these similar because the angles are equal. Okay, there are two ways to prove similarity, either equal angles or sides in proportion. But seeing as I didn't know anything about side lengths, I couldn't go that route. Okay, now what we do is we have to write our statement. So therefore, and the order is essential. So in your opening line, you literally just name the triangles, but in your closing line, you need to get the order right. So we said A, C, B, and that's what we need to write now. A, C, B is similar to triangle E, C, D. Okay, so important because we can use this order just now to figure out the sides that will be in proportion. Okay, and then we need to give a reason, and the reason here was angle, angle, angle. Okay, I'm using the angle sign. You can, if you want to, use A for angle. 100% fine. Okay, why is the order important? Because now what I can do, so we would have stopped there in grade 9, but now at matric level we actually want the proportion. So what I'm going to do is I'm going to take the first two letters of each, and I'm going to say AC over EC is equal to the second two letters of each, CB over CD is equal to the first and third letters of each, AB over ED. And so what I've done now is I've created some kind of proportions, and these can help me solve a whole lot of information. So now that our foundations are in place, let's have a look at this similarity theorem in action. So in this example, we have got a circle, a big triangle, and a small triangle. Generally, our questions will have a whole lot of writing, and then it's good to read through that and check that all the information is already on the sketch. But in this case, we're just jumping straight to the prove. Prove that, let's get some colors here, AE, so that's this whole side here, over AB is equal to DE, that's this one here, over BC, that one there. Okay, so I like to do that because it just helps me to think, okay, what am I working with? And generally when stuff like this is given to us without any other proportion, our mind should jump to let's prove similar triangles. Okay, now I'd like to complete these triangles and say, well then here's a yellow triangle, the big one, and here's a blue triangle, the small one. Okay, so we want to prove similarity there. Okay, so opening line is to say in triangle ABC for blue and triangle ADE for yellow. Okay, and then remember the order is so important. Okay, the first thing I notice is that this angle A here belongs to both of them. So that can be my first reason. Angle A is common. Okay, and that's almost like a statement and a reason in one. So you could write angle A equals angle A and then in brackets common, but it is acceptable to just write it as one sentence like that. Okay, the next thing that I'm noticing here is that I've got 1, 2, 3, 4 points on the circumference of a circle. So I've got a cyclic quad there, this figure here, and we know something about a cyclic quad. We know that the exterior angle is equal to the opposite interior angle. So we can definitely write that then. Blue triangle is first, so C1 is equal to angle D, exterior angle of a cyclic quad. And then we could prove that thing again, or we could say third angle of a triangle. Let's just for fun say, well, here's another exterior angle of a cyclic quad. I mean, if we can see it, we may as well prove it. So I'm going to say angle B1 is equal to angle E, exterior angle of a cyclic quad. And so therefore, now they are similar and the order is so important. I'm going to say ACB for the first one, ACB. Do you see why I had to write the blue triangle first? Because otherwise this is not going to work. Is similar to triangle ADE. Reason, angle, angle, angle. Okay, and then because they are equal, I can draw some conclusions. Therefore, I take the first two letters, AC, over the first two letters in the second triangle, AD, is equal to second two letters, CB, over DE, and then first and third letter, AB, over AE. And now what I like to do is I like to just look for what they want. So they want AE, there it is. They want AB, there it is. This is coming together beautifully. They want DE, there it is. They want BC. We've written CB, but that's okay. So there, essentially, we've proved it without having to do any more work. Sometimes we have to do a little bit more. Okay, but ours is just upside down. So I'm going to rewrite it then. And that's okay. If it's in proportion, it's okay, as long as you change both sides of your equal sign. Okay, and so therefore, AE over AB is equal to DE over BC. And the reason, we had similar triangles. Let's take a look at another example. In the sketch below, AC bisects angle A. What does that mean? That means that A1 is equal to A2. Okay, prove that BC squared, let's get some highlighting here, BC squared is equal to AC times by CE. There we go. Now, I think it's super helpful for you to get into the habit of recognizing that this actually has something to do with similarity. If you have a BC times BC equals AC times CE, you could almost try to picture the step before where you cross multiplied. So you would have taken the numerator on one side, multiplied by the denominator on the other side, and then the denominator on one side multiplied by the numerator on the other side. Okay, if you can try and picture it like that, because then if you times that, you get BC squared, and if you times that, you get AC times CE. Okay, and this just helps me to think, is there a triangle BCE? BCE, there is one, okay? And is there a triangle ACB? ACB, there is one. Okay, so there, with not too much effort, just a bit of logical deduction, I've actually figured out, this is probably a similarity question in those two triangles. So BCE is going to be this triangle here, and then let's in blue do the other one there. I think this is going to take some thinking from us, but at least we've got our two triangles narrowed down. So in triangle ABC and triangle EBC. Okay, we're going to start now. I've written the blue triangle first. Okay, the one thing that's always easy for me to spot is a common angle. They both at least have a C, so let's write that as our first statement. Angle C is common. Okay, now the next thing I start looking for is, this is in a circle, so maybe it's a cyclic quad, because as it stands now, I can't find something that this angle is equal to. This has not been given to us as the center. And if you look at it, it looks a little bit off center, so it probably isn't the center. Not that these things are drawn to scale, so don't quote me on that. But they have given us these x's here, which might mean something. So let's see if we start highlighting potential cyclic quads. So there, those are 4 points on the circumference. That's all I need to make a cyclic quad. Okay, and then what I've got, if you look with me, is yes, angle C is going to be equal to angle D, but that doesn't help me. Angle D is not in any triangle that I'm working in. But what about an upside down one? This angle A here is going to equal angle B2, and at least that's also equal to x. Okay, so I'm going to start listing my logic here. I want to have, let me color code these. A, B, C was by blue triangle. Blue triangle first, and yellow triangle second. Okay, and I can say in my blue triangle, oh, this is not even in the blue triangle. Okay, I'm not ready to make statement 2 yet, but what I am ready to say is that angle A1 is equal to angle B2, and the reason they're angles in the same segment. All right, but we were told that A1 is equal to A2 because they told us that it's bisecting. Okay, that was given. And so look at this logic. Because they're both A1s, that means automatically those ones are equal. So therefore angle B2, I'm going to list it the other way around. Why? Because I want my blue triangle first. So I'm going to say angle A2 from the blue triangle is equal to angle B2. And that's going to be our second equal angle there. And once we've got two angles equal, we can therefore assume the third angle is equal. So let's just make sure we've used this one and this one. So what's left? We've got the big angle B in the blue triangle, and we've got this angle E here in the yellow triangle. So I'm going to write it down as angle ABC. Okay, you could also say B1 plus B2, that's fine, is equal to angle E3. Why? It's the third angle of a triangle. Okay, because everything's going to add up to 180, they have to be equal. And so therefore, now we've got similar triangles. Okay. CAB is similar to triangle CBE. Okay, angle, angle, angle. And what can we deduce? Therefore, CA, first two letters over first two letters, is equal to second two letters over second two letters is equal to the first and the last over the first and the last. And the reason? Similar triangles. Okay, and now let's have a look at what we need. We need BCs, so let's identify them. There's one and there's one. And we need an AC, okay, there's one, back to front, but that's okay, and an EC, or CE, there it is. All right, this is coming together beautifully. So I'm just going to take those two, and I'm going to say, let's write them alphabetically like they are in the goal there, the question. AC over BC is equal to BC over CE. So I'm just writing alphabetically. And now I'm going to cross multiply. So denominator on this side times the numerator on that side. BC times BC is equal to numerator on this side times denominator on that side. AC times CE. And there we've answered their question. Okay, so very important. Get your order right. Blue triangle, then yellow triangle, because that leads to your order being right here. Okay, and then in your initial step, just to make sure you're getting the right sides in proportion, I strongly advise you follow my first two letters, second two letters, first and third letters. Okay, but then once you need to answer the question or match your proof, then you can just change the order. Side CA is the same side as side AC. So that's okay to change the order in this step, just to make sure that your wording or your letters match exactly what you've been asked to do.